Hello, Mr. Claudia here. Today we are going to return to the topic of differential calculus. We have two chapters where we're going to look at some of the powerful applications of calculus. This first chapter is called curve sketching. Curve sketching is a really neat thing that we're able to do with the aid of calculus. By the end of this chapter, we're going to be able to sketch any curve, any function. Now, so far, we've been preparing you for this chapter your whole math career. So far, you should be able to find domain and range. If I were to give you an equation, you could find the domain and range. And you could also find the x and y intercepts. Hopefully, you remember how to do that. For the x-intercepts, you set y equal to 0. For the y-intercept, you set x equal to 0. Those are the things you can do so far. Now, in this chapter, we're going to teach you a bunch of extra things. How to find out when a function's increasing or decreasing, how to find the max-min points, the asymptotes, which we have talked about a little bit already, concavity, or in our previous units, concavity, which we haven't learned, and points of inflection. With all this information, as I said, by the end of the chapter, in about 5 lessons, I'll be able to give you a curve like this, and you'll be able to sketch it all for me. Takes about 30 minutes, but you'll be able to sketch it perfectly. So that's where we're going. So let's start with the first new thing we need to teach you. How do we know if a function is increasing or decreasing? Now, it'll be a second before we get to the actual calculus, which is good because I know we haven't done calculus in a while. But what does it mean if something's increasing or decreasing? Well, that means, just like it sounds, if you move from left to right, if something is increasing, if you move from left to right, the y values are going up. I'll look at the second one. So this is the stock market. In general, over time, the stock market always goes up. Even though there are big drops that happen, the Great Depression, the Great Recession, in general, if you looked at it over a long period of time, it's a kind of an increasing function. A decreasing function is the opposite. As the x values go up, the y values go down. So here I have, so x1 is less than x2. So let's say this, let me use a different color pen here. So let's say I choose this point. So I know this point has some x value. We'll call it x1. And I'll choose this point. This point has some x value. We'll call it x2. x1 is less than x2. And a function is decreasing if f at x1, so that is the y value, f at the sub in the value of x1 is greater than the y value at x2. So really this is just kind of math speak for what we have known since grade 9. A graph that's going down or pointing down is decreasing. A graph that's going up is increasing. And this is the similar language. It's just hard to draw in this picture. So we know graphically that a function is increasing or decreasing. What we need to figure out is how do I know if this function, where is it increasing, where is it decreasing? So that's what we're going to get to. But first, let's look at this example here. So given the following function, determine the intervals where f at x is increasing and decreasing and draw the derivative function. Okay, so let's look at this graph. In fact, what we could do, I'm just going to write it off to the side. F at x is increasing. Okay, so again, you could use your math definition, or we should just be able to look at it and see the graph is going down here. Oh, it's going up here. Let's say this is -1, -2, -3, and this is 1, 2, 3. So I would say that f at x, this function, is increasing between 1 and -1. And if you hopefully remember, the way we write intervals like that is x is greater than -1 and x is less than 1. So I write x is between -1 and 1. This kind of format is very common when we're talking about ranges. Similarly, we can say that f at x is decreasing. Well, if I look at this graph, it's going down here. So from -infinity all the way to -1. So that is x is less than -1. Anything less than -1, the graph is going down. And anything greater than 1, the graph is going down. So those two ranges as well. So again, graphically, it's not too difficult to figure out where something is increasing or decreasing. We could actually represent these intervals on a sign diagram. I'm just going to draw this thing for you because we're going to be using it on the next page. But what if I represented all of the x values with a line? And we know that this is -1 here and there's 1 here. So I know that it's decreasing in this region, it's increasing in this region, and it's decreasing on this region. So that's a sign diagram. We're going to figure out how to draw this on the next page. Part B, draw the derivative function. Now this can be a little bit challenging. This is more of a conceptual question about the derivative. And I know it's been a long time since you've done the derivative, but it's a good thing and it helps set us up for a little bit later in the chapter. Okay, so the derivative here, well, we know that the derivative, and we're going to get to this on the next page, but when a function is increasing, we know it has a positive slope. So we know that between -1 and 1, the function is positive. So it's somewhere up here. It's in the it's a positive function. And then here we know the function is decreasing, so we know that the derivative, if I'm drawing the derivative, it would be negative. It would be below the x-axis. We know that these points, -1 and 1, it's neither increasing nor decreasing. So my derivative is 0. So if I fill in kind of the blanks here, then I have something like this. This is my derivative function. Again, between less than -1 and greater than 1, my derivative is negative. It's negative because the slope is negative. And similarly, in this region, the derivative is positive, which means it's a positive slope. Remember, derivative is really telling you what the slope is. This is a big jump, and this is what we're going to be doing kind of at the end of the chapter, questions that look like this. Okay, let's turn la page. Okay, so how can we figure out if a function is increasing or decreasing by looking at its the equation? Well, we just talked about it. If the derivative is greater than 0, then the function is increasing. If you want to think about that, in this section, for example, if I were to draw the tangent line, which is what the derivative is. So if I draw a tangent line in this region, the slope of the tangent, m tangent, is positive. Therefore, the derivative is positive. It's greater than 0. So for an increasing, to know if something's increasing, the derivative is positive. Similarly, for a region like this where the function is clearly decreasing, it's going down, we can see that m tangent, the slope of the tangent, is negative. Therefore, the derivative is less than 0, or it's negative. So if the derivative is greater than 0, or the slope of the tangent is positive, then f is increasing. If the derivative is less than 0, that is, if the slope of the tangent is negative, then the function is decreasing. What about these points where the derivative is 0? Where the slope is 0? Again, hopefully you remember, point like this this min point, this is where the slope is 0. Or the derivative is 0. We call points like that the critical point, or critical number. And we'll talk more about those in our next lesson. Really, all we care about today is how do I know if something's increasing or decreasing? Well, I have to look at the derivative. So let's say I give you a function like this. Tell me, where is the function increasing and where is it decreasing? Well, what I really want to do is to be able to draw a sign diagram like I had here. So I can tell you, oh, it's increasing here, it's decreasing there. But to do that, first I need to find the derivative, because as we just said, you need to find the increasing or decreasing regions, you have to find the derivative. So here, hopefully you remember, how do we find the derivative? F prime at x. Hopefully you remember the power rule, where I subtract 1 from the exponent and I bring the exponent down. So I get 3x squared plus 12x plus 9. It's just like riding a bike. It comes back to us. We never forget how to take a derivative like that. Now, what we want to do, now we have some sort of trinomial. What do I want to do? Well, I want to figure out all these critical numbers, all these points where I change from negative to positive. So we're going to say there are, well, first let's factor the result. Hopefully you remember how to factor. I'm going to factor out the 3. That's the easiest thing. So I have a simple trinomial, x squared plus 4x plus 3. And then I can factor that further. X plus 1. X plus 3. Okay, so now we want to find the critical points, so the critical numbers. So find the critical points which occur when f prime at x equals 0 and f prime at x does not exist. So in our case, it's actually pretty straightforward. There is no f prime at x not existing, because this is a nice polynomial function. But I can find where it equals 0. So I'm going to set this derivative equal to 0. So then I have two answers. I have x is equal to -1 and x is equal to -3. Those are the two places where this statement is true. So those are my two critical numbers. Remember, the critical number is sort of like a dividing line between a region that's increasing and a region that's decreasing. So now, remember, my goal is to draw this sort of sign diagram type thing. Well, now I almost am there. The sign diagram is going to look like this. And I'm going to write the sign of f prime at x, of the derivative. And we know that it's broken up by these two critical points, -1, -3, and -1. It's like a number line, so it goes from -infinity to positive infinity. Okay, so now I have to figure out, okay, well, what's happening less than -3, what's happening between -3 and -1, and what's happening between, or greater than -1. We can analyze this by using a table. I find this is the quickest way. So to analyze where f prime at x is positive and negative, we make a table of all the factors in f prime at x. So we're going to make a table, and this is a common thing that we're going to be doing a lot over the next little while, so you're going to get used to doing this. But basically I'm going to draw these three intervals in my table. So I'll do it like this. So I have 3 intervals plus my heading. So I have this. 1. That should be good. Let's draw everything. Let's leave it like that. That should be okay. All right, so this, bear with me. So you're going to write along the top the different intervals. So I have x is less than -3. I have x is between -3 and -1. And I have x is greater than -1. Again, we're going to get used to this format, but these are the way we write these different ranges. Notice that we're never saying x is equal to -3. We know that that's a critical number, so we're not interested in that right now. On the left-hand side, I'm going to write all the factors of the derivative. So where's my derivative? Oh, here it is. I've already factored it, which is great. So one of my factors is 3. Another one is x plus 1. And the third one is x plus 3. Okay, so I'm just going to label this. So along here, I write the factors of f prime at x. And then along here, I write the intervals, which I didn't really allocate my space very well. Okay, so now watch how this works. This is really neat. This is the sign. What we're trying to do is figure out the sign of the derivative of each of these 3 regions. So what you're going to do is choose a number that is in this range, less than -3. What's a number that's less than -3? Don't overthink it. Choose something that's easy to do the math for. You cannot choose -3 because that's not less than -3. So why don't we try x is equal to -4? You don't have to write this, what we're trying. I'm just showing you the strategy for the first time we do this. So now we think through, for these 3 factors, what happens when x is -4? Well, the 3 is positive. Nothing happens. What about x plus 1? Well, -4 plus 1 is -3, so it's still negative. What about -4 plus 3? Still negative. So now my factors, x plus 1, x plus 3, when I multiply these together, I get a plus times a minus, which is minus, and then a minus times a minus, which is positive. So this becomes plus. So I can even write out kind of this. I'm just going to write out the steps once. You don't have to show this step. So this becomes positive. So that is my result. We have to do the same thing with the other interval. Here you can choose something between -2 and -1. You choose something easy. How about x is equal to -2? This is going to always be positive. This is going to be -2 plus 1, which is still negative. This is going to be -2 plus 3, which is now positive. A positive times a minus is minus, times another positive is minus. So minus. And try a number greater than -1. Well, let's try x equals 0. So if I put that in, this is going to be positive. This will be positive. This will be positive. So this will be positive. Okay, so look what we've done. We've tried these different values, and we've been able to figure out the sign of the derivative, right? This result is the sign of f prime at x. So this is what we were looking for. Remember, we were looking where is the sign positive, because that means that the function's increasing. The negative means decreasing, and then it's increasing again. What I recommend doing is going back and labeling your sign diagram. We have a positive region here, a negative region here, and a positive region here. Just to be complete for this solution, I'm going to write, therefore, the function is increasing for x is less than -3 and x is greater than -1, and decreasing for x is between -3 and -1. Wow, amazing. So now for the first time ever, you can take this and you can at least sketch the areas where it's increasing, decreasing, increasing. That's about it. But again, we're going to learn a lot more stuff over the next few days. Okay, I don't think I have any other things to tell you. Why don't we move on to the next example, and we'll look at how to do this a little quicker. Not all examples are going to be beautiful polynomial functions like this. One type that we're always going to see is a rational function like this. But we follow the same strategy. So how do I know where this function is increasing or decreasing? Well, I need to find the derivative. So, oh my god, hopefully you remember how to do derivatives of things like this. You have to use something called the quotient rule. The quotient rule is derivative of the first thing, which is derivative of 5, which is 0, times the bottom thing, which is x squared minus x minus 20, minus the first thing, which is 5, times the derivative of the bottom thing, which is 2x minus 1, all over the derivative squared. You thought the chain rule was done. Well, it's not. Or sorry, this isn't the chain rule. Oh, don't get ahead of ourselves. This is the quotient rule. Okay, now I can simplify this a little bit. This cancels out because it's multiplied by 0. So I end up with negative 5 times 2x minus 1. Okay, over x squared minus x minus 20. Might as well factor that since I'm right here. So I'm going to have x minus 5, x plus 4. And that whole thing I'm going to square. And we're just going to say that it is useful to factor. The denominator. Okay, so now I have the factored version of my derivative. What did I do last time? Oh yeah, I had to find the critical points, or the critical numbers. To do that, I have to set the derivative equal to 0. So I'm going to find critical numbers by setting f prime at x equal to 0. So I'm going to say 0 is equal to negative 5 2x minus 1 over x minus 5 x plus 4 squared. Oh, it's hard to see. Okay. And now, okay, so how do I solve this? Well, first thing I'm going to do is cross multiply. So remember, this is technically 0 over 1. So when I cross multiply, I get 0 times this, and I got 1 times this. So I end up with 0 is equal to negative 5 2x minus 1. Well, that was easy. Now I want to simplify this. I'm going to divide both sides by negative 5. So I end up with 0 is equal to 2x minus 1. I bring the 1 to the other side. 1 is equal to 2x. So x is equal to half. Whew. So that is one of my critical numbers. Now, that's not it, right? Because last time we said also we have to find where the derivative does not exist. Now, for a nice polynomial function like up here, it always exists. But we know for rational numbers, rational functions, it's not true. There are some places where the function doesn't exist. There's asymptotes or holes. These are often due to the divide by 0 issue with the denominator. So to find the other critical points, I'm going to do another calculation over here. There are also critical numbers when f prime at x does not exist. That is, the denominator is equal to 0. So I take the denominator of to find a place where this function, the derivative, does not exist. That's a place where the denominator is equal to 0. So I'm going to set my denominator equal to 0. So I have x minus 5, x plus 4, all squared, technically that's x minus 5 squared and x plus 4 squared. For this to be true, this has to be either, ooh, why did I do a different color? Oh, that's a nice color. Either we have x equals 5, which would make this statement true, or x is equal to negative 4. So now I have 3 critical points. I have x equals negative 4, x equals 5, and x equals half. So I'm going to do just what I did last time. These are my critical points. They're kind of the edge cases of my for this question. So I'm going to draw my sign diagram. Sine of f prime at x. And I'm going to draw all of these, I'm going to put all of these critical numbers. So negative 4, half, and 5. It doesn't have to be the scale, but you should put them in order. It is a number line from negative to positive. So these are my critical numbers. I want to figure out what happens in between them. So just like I did last time, I'm going to make a big table. This time there are 1, 2, 3, 4 columns plus the column on to list everything. So I'm going to draw this out like this. So I have the column for all my factors. And there are a lot of factors. I'll make this one longer. Then I need 4 columns. So 1, 2, 3, 4. Oh, could be better. Okay, and my different intervals are x is less than negative 4, x is between negative 4 and half, x is between half and 5, and x is greater than 5. Remember, we don't do equal to, we just do the in between. Now I have to list all of my factors of the derivative on this side here. So I go back to my derivative, there it is, and I'm going to list all the factors. So list them all. So I have negative 5, that's a factor. Then I have 2x minus 1. Then I end up with, okay, it was x minus 5 squared, so I'm going to write that. And x plus 4 squared. Those are all of my factors. For this system to work, you have to be complete, you have to put them all in. Okay, so there's my factors, and I'm going to write my result here. So same strategy as I did above. Let me choose some numbers in these ranges. So choose a number that's less than negative 5, again, or negative 4. So let's choose negative 5. You don't need to write it out, you just need to write out the signs. Actually, before we get started, negative 5, no value of x is ever going to change this. It's always going to be negative. So let me just label that right off the bat. Okay, let's choose a number that's less than negative 4, negative 5. If I put it in here, I end up with 2 times negative 4, which is negative 10 minus, okay, so it's minus. Negative 5 minus 5 is minus 10. I square it, I get a positive. Negative 5 plus 4 is negative, but I square it, I get a positive. In fact, these two are always going to be positive. Because no matter what x value I put in here, I'm always squaring my result. So if it's a negative or a positive, I always square it, I end up with a positive. Let's look at this number. Okay, choose a number between negative 4 and half. Oh, this should be easy. I'll just choose 0. If I put a 0 in here, it's negative. Choose a number between half and 5. I'm going to choose 1. That'll be the easiest number to use. 2 times 1 is 2 minus 1. That's positive. And if I choose a number greater than 5, say 6, this is also positive. Okay, now what you end up with, if you go back to what your function looked like, I had the negative times a negative over a positive times a positive. Let's think this through. So negative times negative is positive. Divided by 2 positives, this gives me positive. But let me give you a shortcut. Count the number of negative signs. This is a lot easier. If you have an even number of negative signs, then your answer is positive. If you have an odd number of negative signs, your answer is negative. So that's a little shortcut. We're going to put that in a little bubble. This is a great way to deal with these sign diagrams. It's just important that you list all the factors, including these coefficients here. So 2 negative signs means it's positive. 2 negative signs means it's positive. 1 negative sign is odd, that's a negative. 1 negative sign is negative. So now I can go and label my sign diagram up here. I have a region that's plus, plus, minus, and minus. So therefore, the original function f of x is increasing for x is less than -4 and x is between -4 and half, because those are the two regions where my derivative is positive. And f of x is decreasing for x is between half and 5 and x is greater than 5. You might be asking, well, how come, how do I know that, what about at -4 or at half? And those are critical numbers where the function is neither increasing nor decreasing. So don't worry about those. Make sure you write your intervals like that. That is it for our increasing and decreasing functions lesson. That's the first step in being an expert at curve sketching. Your homework for tonight is page 232, number 1 to 10. Hopefully it will also be a bit of a review of how to do the derivative. Good luck with that, and we'll see you next time.